All right, so moving along, looking at work and power in a circuit. So remember, everything that we've been working with in circuitry has come from the conservation of energy, which means we can bring in concepts like work and power. So if we recall, work is equal to F dot R, so force applied over a distance, or F dot dl. You might have also seen that. Okay, so it would follow that if you have a charge Q and you move it to here, so now Q is here, you must do work on Q. Okay, so now let's think about this in terms of electric potential energy. And delta V. So the change in electric potential energy of this action is delta U. And so delta U E is going to be equal to delta Q times delta V, which we've seen before. And then to get power, we need to factor in time. Because power is equal to energy per unit time. So power is equal to delta UE over delta T, which is delta Q times delta V over delta T. All right, so building on that, let's bring in some things that we already know. So delta Q over delta T is charged moved per unit time. But we've seen something that is charges per unit time, and of course delta Q over delta T, which is also just FYI dQ dt, is equal to current, which is coulombs per second. So therefore, power is equal to I delta V in circuit. So let's think about power dissipation in a resistor. So I is equal to delta V over R. Then it follows power is equal to I times IR is equal to I squared R, or we could write it power is equal to delta V over R times delta V is equal to delta V squared R. And as for which expression you use, well, what information do you have? And that will take you in the right direction. Okay, so let's analyze a circuit with all of the information that we know. So in this circuit, we have two 9-volt batteries. We have a light bulb. Another light bulb. So let's say we have 15 ohms of resistance here, 75 ohms of resistance here. Let's look at a couple spots. We can look at A, B, C, D, E. And this is a low resistance wire. Okay, so if you're given a problem like this, the first thing I would recommend you do is to redraw it. This is kind of yucky. We now know circuit conventions, so let's go ahead and redraw it using nice, clean circuit conventions. So here's battery 1, battery 2, resistance 1, resistance 2. Okay, so we have got 9 volts, 15 ohms, 75 ohms. We have F, A, B, C, D, E. Okay, so now we've replicated the circuit using a much cleaner drawing. So we're going to assume steady state. And what we want to do is we want to calculate the electrons per second flowing out of the battery. So that would be location A. So to do this, we're going to need loop rule. So we would have twice the EMF minus IR 15 ohms minus IR 75 ohms. Remember, these are all the voltage drops, is equal to 0. And what we're going to do, we've got all the information to calculate conventional current, so we're going to find conventional current I and use to get little I. Okay, so now that we have our plan of attack, let's go ahead and implement it. So I is equal to delta V over R. In this case, we've got two in circuits, so our EQ is going to be R1 plus R2. We'll just plug that in, say I is equal to twice the EMF over R15 plus R75 is equal to twice 9 volts over 15 ohms plus 75 ohms. So I is equal to 0.2 amps. And little I is equal to I over Q. And this, of course, comes from I is equal to QI. And so we get that little I is equal to 0.2 amps over 1.6 times 10 to the minus 19 coulombs, which is equal to 1.25 times 10 to the 18 electrons per second. Okay, so now we've calculated the amount leaving per second. Let's think about the surface charge if we go around that circuit. I'm just going to reuse my drawing that I already have. And so we would expect that here we've got a resistor, so we're going to need a bigger field. To get that over, it's going to start to dilute. Here we're going to have a small gradient of charge. So that's the surface charge. You've got big, great, a lot around the batteries. You've got big fields needed to get it over the resistors, and then it dilutes out. Okay, so moving on, we can think about the potential going around the circuit. So I is constant, it's steady state. So from A to B, you just have wire, so it stays the same. Then you go over the resistor from B to C, and then you've got more straight wire till you get to D, and then you have a big resistor to E, and then more straight wire to F, and then it drops back down by the battery when you get back to A. So that would be the potential. All right, so next up, let's calculate the electric field across the first filament. Okay, so for this, you need a few more values. So let's say the length is approximately 5 millimeters, and the cross-sectional area is approximately 5.1 times 10 to the minus 8 meters squared. So what is the electric field given these values? So E is equal to delta V over L, which is equal to R15 I over L, which is equal to 15 ohms times 0.2 amps divided by 5 times 10 to the minus 3 meters. And so the electric field is approximately 600 volts per meter. So now we can go after the power of our batteries. So power is equal to I delta V is equal to 0.2 amps times 9 volts. And power for one battery would be 1.8 watts. And then you would just double that for the second battery.